Okay, now that we've looked at bank balance sheets, let's start looking at models of banks. And in particular, we're going to do something called the Diamond-Dybvig Bank. And the Diamond-Dybvig Bank is a model of a bank that's going to try to talk to us about the incentives banks face, regulation of banks, and why banks are dangerous. And the core of why banks are dangerous always comes back to this idea of assets and liabilities mismatch, right? The bank is funded largely by deposits, and deposits are something that consumers can come back and get at any time. But banks make loans, and many of these loans are not super liquid and cannot be sort of gotten back at any time. And so we're going to take time really seriously here. We're going to have 3 periods in this model. And we're going to take time as relates to investment really seriously. So we can make investments at the beginning of this game, and we can invest 1 unit, and then we can get our units out if we let the investment percolate through to maturity. But that takes time. Investments, real, tangible, physical investments, whether they're building factories, putting up windmills, or anything else, takes time to complete. And so we might need to give this investment real time to mature and to actually earn interest. But the real world here is going to interfere through this parameter gamma, which is the liquidity parameter. Liquidity, sorry about that. The gamma here reflects basically the probability that something happens in your life that causes demand for cash. Lots of things happen. People get sick, people have weddings, good and bad things. But all these unexpected events might cause you to need cash. So this is the probability you need cash at t equals 1. And if you need cash at t equals 1, you get only salvage your initial investment. You get no interest whatsoever. And this is going to be at the core of the Diamond-Dybvig model. So investments take a long period of time to complete, but sometimes life gets in the way. And consumers don't like this. If they were left to their own devices, this is not super great, right? If we were to draw our normal C1, C2 problem here, C2, C1, it would look something like this, right? The investment technology that consumers have access to offers them a very basic choice, right? You can get 1 today if you need your cash, and you can get R tomorrow. And people don't really like this because it's risky. It's really risky. If 1 and R are very different, right, you can think of that as very bad consumption smoothing. If 1 and R are significantly different, and R might be quite greater than 1, right, this is not like a bond, this is a physical investment, then we are taking on substantial risk that we're not doing anything about. We don't know whether we're going to be hit with this cash shock at all. We might know whether gamma is 0.2 or 0.4, but even if I know, say, there's a 20% chance or a 40% chance I'm going to need cash, there's no way for me to tell, am I going to be in the 40% or the 60%? So enter the bank. The bank in Diamond-Dybvig can manage risk. And the bank is going to manage risk by pooling deposits. Right? And the bank is basically going to say, look, if we take a whole bunch of people and jam them together, on average, gamma fraction of them are always going to need cash. And we can sort of use the law of large numbers to sort of provide a population with certainty in a way that the individual could never get certainty. And let's think about this. So the bank is going to take a whole bunch of people's deposits, and then it's going to make them promises. And it's going to promise people basically an insurance contract. It's going to say, if you need cash, in the first period, we'll give you C1. And if you need cash in the second period, we'll give you C2. And in particular, those things don't need to be equal to 1 and R. Let's see why. Well, let's write the budget constraint for the bank. In the first period, the bank is going to have to pay out gamma C1 in cash. Gamma fraction of the bank's customers show up, and they all need to be paid C1 according to what the bank promised. And then the second period, 1 minus gamma of the bank's customers, everyone else shows up, and they have to get paid C2, which the bank promised. So let's think about how the bank meets that need for cash. I'm going to call A the fraction of projects that get interrupted. Right? The bank, to meet the need for cash, is going to have to interrupt some of the investments. Right? It's promised people cash at the time period 1 if they get hit by this liquidity shock. And then some of them will, and the bank will have to cash out these investments to meet their needs. The remainder of the bank's obligations, the 1 minus gamma C2, can wait. The bank can wait till the future, cash out other investments, the remainder of its investments at R, and use that cash to sort of meet those needs. So let's add these things together. If we add them together, I get gamma C1 plus 1 minus gamma C2 is equal to A plus 1 minus AR. And if I do my little differentiation here, I can do DC2, DC1 equals minus gamma over 1 minus gamma. So the bank's budget constraint here looks something like this, right? Going through that point. 1 minus R has got to be achievable for the bank. If the individual can get 1 minus R, the bank can promise them 1 minus R. But in general, they might be able to do better, right? Imagine the indifference curves were something like this. If someone's indifference curves were somewhat like this, the bank can promise them C1, C2 by pooling risk across a large number of clients in a way that might make them better off from going it alone.